Welcome to our first lab on conversion factors and problem solving. So in this lab, we're going to see how to convert units from one to the other. We're going to look at how to um, compare or examine numbers for significant figures, and then how to treat those numbers when we do calculations. In other words, how do we give our answers to a particular precision, or when our calculator spits out a whole bunch of decimal places, at what point do we cut off the number and write down that as our answer? Okay, so we're going to start off here. Now, this is a lab that you can do at home. There are some conversion factors where we're going to play around with measuring things in metric units, and you're going to do conversions from regular English units into metric units. And these are measurements that you can make with just household items. So even though we're in the middle of a pandemic and we're not going to get any lab time, this is an opportunity for you to try and measure things at home and pick up some of those measurement skills, the ability to make measurements yourself. So let's scroll on down. I'm not going to spend a lot of time talking about the pre-lab problems or the post-lab problems. Let you, leave it up to your individual instructor to decide whether or not, how you want to tackle those. And most of them are relatively straightforward. So if we have later labs where those might need some extra explanation, I'll go into that. But for this lab, I think they're pretty straightforward, so I'll leave it there. With the experimental procedure itself, I recommend reading through when you're doing your lab. Sometimes students tend to look just at the lab report itself, just where you write stuff in, and it's not always really clear what you're trying to do there. The instructions really help you out in that respect. So I think Part A is a good example of this. If you just look at the table in Part A down on page, let's see, what page is that? Page 8. When you just look at this table, it's not immediately obvious what you're trying to do. But if we go back to the instructions on page 5, it kind of explains the background behind what's going on. Like the numbers in the table are from another student trying to write these numbers out and trying to round them off. And you're assessing whether the student is doing that correctly or not. Okay, so let's go ahead and get started with that part of the lab. So I'm just going to walk through each section of the lab just so you have an idea of what you're doing. But yeah, hopefully this will be relatively straightforward for doing on your own once you've seen a couple of examples of each. So for this example here, you can see that the student's written 143, or sorry, the number the student had to tackle was 143.63212. Now, if we go back to those instructions, you'll see that the student's trying to write this down to 3 significant figures. Okay, so go back to lecture and try to understand what are significant figures, what makes figures significant. Remember, these are non-zero digits, and if you have any zeros in the number, you've got to think about whether those zeros are significant or not. So you kind of have to look whether your zero is a leading zero to the left of the number, a trailing zero to the right of the number, and or a trapped zero in between non-zero digits. Now, this example over here doesn't have any zeros in it, so that makes this much more straightforward. All of the digits listed can be determined pretty quickly whether they're significant or not. So if we want to give this to 3 significant figures, counting from the left, we want that 1, the 4, and the 3 to count. Now, to determine whether we round up or not, since we're cutting the number off after that 3, we then have to look at that next digit, that 6 over there, to determine, is this number going to round up or not? Well, if you have a 5 or greater, the number rounds up, and if it's lower than 5, it doesn't. So since that's a 6, that 143 rounds up to 144, which is what the student wrote down, and therefore the student is correct. Okay, so that's kind of all you have to do. You don't have to write anything over here because, well, it's correct, so you don't need to correct it. Okay, so you need to go on and continue that. I'll do one more example just to help make this a little bit more clear, especially since we've got an example here that does have zeros in it. So if we look at this number over here, 532,800. Okay, so again, we want our significant figures here, the 5, the 3, and the 2. Like those 3 digits are important. And then we look at that next digit, that 8, and we say, all right, we're going to have to round up because that's, 5 or greater. So that 2 becomes a 3. Now, the student was thinking along those lines, and they wrote 533. But there's something that's a little bit off with this answer. Okay, see if you can figure out what it is. It might be easier to figure this out when you say the number out loud. This is 532,800, okay, a very large number. And the student has just written out 533, okay? So notice that the sort of placeholders that puts this in the thousands place is missing, right? The scale of the number has been reduced down. Okay, so that should be kind of weird. If you're having trouble seeing why this is a logical flaw, try writing this number out in scientific notation. If you have 532,800 and you wrote it out in scientific notation, that would be 5.328, and we move that decimal point 1, 2, 3, 4, 5 places. So 5.328 times 10 to the power of 5. Oops. 10 to the power of 5. And now, if we want to change that to 3 significant figures, we basically make that, again, we take into account that 5, 3, and that 2, and because of that 8, we round up. So to 3 significant figures, the answer becomes, I'm going to write that over here, 5.33 times 10 to the power of 8. Oh, sorry, 10 to the power of 5. And again, notice that here we have our 3 significant figures. That 5, the 3, and the 3 are significant, and there's no significant figures after that, that coefficient. So if I were to write this out in standard form, which is what the student was trying to do, what would that number be? Well, remember, when you're going from scientific notation into standard form, you just move your decimal place based on the exponent that's listed over here. Okay, so we're going to move this 5 decimal places to the right. So we'd move that 1 place here, another place here, and now we've reached the end of that coefficient, but we still have 3 more spaces to move that decimal point. So you're going to put in placeholder zeros for that number, and that's where the actual answer comes in. So the student is wrong here. What they should have written was 533,000, because that's where those 5 decimal places, the 5 places down you're moving due to that exponent of 5, it comes in. Okay, so the decimal point is moved, is kind of listed here kind of imaginarily, but it's 5 spaces away from where the decimal point in your coefficient is when you write in scientific notation. Okay? All right, so again, I'm going to let you do the last 2 yourselves, but this one's a common mistake I think a lot of students make, so it's something to watch out for when it comes to scientific notation, to significant figures. Ask if the number written out that's rounded off, if it still makes sense in context with the original number, okay? And again, saying this out loud is probably a good way to figure that out. This is 532,800. This is only 533. Okay. So in part B and part C, this is a good example of why significant figures and determining them is really important, okay? Because it helps us determine how to write out these answers when we do calculations. Now, when it comes to calculations, you want to break this down to two different scenarios, and your problem, your lab report does this. In part B1, you're doing multiplication and division problems. All right. When it comes to multiplication and division, you are going to pay attention to the number of significant figures. Okay. When in part B2, we're going to do addition and subtraction problems, and when it comes to those, there we're going to pay attention to the number of decimal places. So that's a common mistake a lot of students make on quizzes. You've got to watch out when you're doing an addition and subtraction. A lot of students will give their answer to the number of significant figures, the lowest number of significant figures, instead of the lowest number of decimal places. Okay, so let's do a practice problem from each of these and figure out how to write out our answers. Okay, so let's use this first problem as an example of how to do a calculation and report our answer to the correct number of digits. So in this first problem, we are multiplying three numbers. Now, you can do this on your calculator easily enough. So let's pull up a calculator. Okay, and if I take 0.1184 and I multiply by 8.00 and I multiply by 0.0345, my calculator spits out the answer 0.0326784. Now, do I have to write down all those digits? And the answer is no. Our exercise here in part B is to figure out where do we cut off the number. Okay, now to do that, you've got to look at the precision of the three numbers in your calculation, and then you're going to give your answer to that lowest precision. Which of those numbers has is the least precise? Your answer can only be as precise as that level of precision. Now, let's go ahead and write out the number of significant figures for each of these numbers and go from there. So going back to the problem, we have 0.1184, okay? So we have a leading zero over here, okay? And we have a 1, a 1, an 8, and a 4. Those are four non-zero digits. So we know that these four digits are significant. They're going to count towards the significant figures of the number. Does this leading zero count? And the answer is no. Remember, leading zeros are never significant. So this number over here has four significant figures. Okay, now let's look at this second number over here. We have 8.00. Well, the 8 is definitely significant as a non-zero digit. Now the question is, do these trailing zeros at the end of the number count? While leading zeros are never significant and trapped zeros are always significant, trailing zeros, I think, are the ones that give students the most problems. They may or may not be significant depending on if the number has a decimal point. Does this number have a decimal point? Yes, it does. And so these zeros will count. The person who wrote down this number wrote those numbers down on purpose, and therefore it means that those zeros were measured and therefore they count. So if that 8 and the two zeros are significant, that means this number has three significant figures. Then let's look at this number over here. We have 0.0345. Well, the 3, the 4, and the 5 are definitely significant as non-zero digits. Do these leading zeros count as significant figures? Remember, leading zeros are never significant, so it's only that 3, that 4, and that 5 that are significant. So this also has only three significant figures. Okay, so which of these numbers has the least number of significant figures? Well, both of these numbers have only three significant figures, and that tells us then that our answer must also be given to three significant figures. So if we go back to our calculator and we see that the number given is 0.0326784, we need to write this number to only three significant figures. Now, what are those three significant figures? Does does this 0 count as a significant figure? Or does this 0 count as a significant figure? And the answer is no. Remember, leading zeros, that's zeros that are to the left of non-zero digits, okay, at the left of our number, are never significant. So our first significant digit is that 3. The second is the 2, and then 6 is also significant. Okay, so there's our 3 significant figures, the 3, the 2, and the 6. Now, do we round that 6 up or not? And to decide that, we're going to look at that 4th digit, the 7, and ask ourselves, is this 5 or greater? And yeah, 7 is greater than 5, so we're going to round up. That 6 is going to round up to 7, so our answer is going to be 0.0327. So let's go ahead and write that. 0, oops, go 0.0327. That would be our answer to 3 significant figures. Okay, so again, when you're doing your calculations, that's how you want to kind of proceed in this type of problem. You want to look at each of the numbers involved in the calculation, ask yourself, how many significant figures does each one of those have? And then when you do your calculation on your calculator, be sure to round off accordingly to the right number of figures. Okay, so let's try something from part B2, which is a very similar type of problem where, except instead of doing a multiplication or a division, we're doing addition and subtraction. So if we look at this first example over here, we are adding together 2 numbers, okay? So again, we can do that on our calculator really straightforwardly, right? I mean, you could probably even do it just on paper, but if we were to take 13.45 and add 0.4552 to that, we would get a total volume of 13.9052, which is great, but we don't need to write all of those decimal places. Your calculation, your answer can only be as precise as the least precise of your measurements that are in the calculation. Now, when it comes to addition, though, we want to look at the number of decimal places. So this actually winds up being a lot easier than the problem with significant figures, with multiplication and division. So let's look at that first number over there, 13.45. How many decimal places do we have after that decimal point? Well, that 4 and the 5 come after, that's 2 decimal places. Okay, now let's look at 0.4552. After our decimal point is the 4552, that's 4 decimal places. So, which of these numbers has a lower level of precision? Well, 2 decimal places is a much fewer number of decimal places. So when it comes to writing out our answer, we can only go to a maximum of 2 decimal places. That is the maximum we can give our answer to. So when we look at our calculation, before our decimal point we have the 13, and that's great, but we can only write down the 9 and the 0 for our decimal places. We can't go any further than that. However, since we're cutting off the number here between the 0 and the 5, ask yourself, do I need to round up this number? So look at that 5. Is it 5 or greater? Well, obviously it's 5 or greater, so we have to round up. So that 0 is going to round up to 1. So our answer winds up being 13.91. And that's how you would write out that answer instead of writing out all the digits from your calculator. Okay, so that's basically how you should approach a problem. If there's a multiplication or division, look at the number of significant figures and give your answer to that to the lowest number of significant figures. And if there's an addition or subtraction, you're going to do the same thing, except you're going to look at the number of decimal places and give your answer to the lowest number of decimal places. Okay. If we don't really do any problems where you have to do both multiplication and division on this lab report, but for those of you who are going to ask that inevitable question, basically do your multiplication and division first. If you think back to math classes where you have the expression PEMDAS, or please excuse my dear Aunt Sally, where you do multiplication and division first, and then you do addition and subtraction afterwards. So basically, when you do your multiplication and division, first write out the number of significant figures, or write your answer to the correct number of significant figures, then use those answers in your addition and subtraction, and then worry about the number of decimal places after that. Okay, so again, you don't stress too much about that. You don't have any problem that complicated on this lab report, but in case any of you were curious, that's how you would approach that. Okay, so in part B3, you want to measure the length and the height, or sorry, the width of this rectangle, and write down your measurements. Since you're going to be doing this alone, where we don't have a lab partner here, don't worry about doing another student's measurements. Just do this section here. So you're going to need a ruler for this, obviously, and you're probably going to need a printout for this. But go ahead and try and measure that out as best as you can, and write out those numbers here. The key thing I'll be grading you on, at least, is the way you write out your calculations. So if you make a mistake in your measurement, it's not the end of the world. I'm kind of just making sure that your area is calculated correctly and you're going to the right number of significant figures. So depending on the scale you're using, you need to write down the appropriate number of decimal places. So for example, if you're measuring, first of all, you need to be measuring these in centimeters, but when you're measuring this, let's say your ruler goes to the nearest millimeter, or the first decimal place on your centimeter scale. So when you measure this, you need to write out that decimal point, that decimal place in your measurements of length and width. Now, to figure out the area, you're doing a multiplication, right? So you need to give that answer to the correct number of significant figures, just like we did in part B1. Okay. Very similarly, the shape of a solid, you can measure any household object. Just take like a box from your pantry, or a tissue box, or just really anything, like a can from your pantry and it's a cylinder. You can use the formula in your pre-lab to calculate the volume of that object accordingly. When you're doing the calculation, though, you're multiplying those dimensions together. So keep that in mind when you're writing out your answer. Okay, so record your measurements according to the right number, according to what your ruler says. Don't round off a measurement. You always want to write out what your measuring device says. And then when you do your calculation, that's where you round off your answer. Round it off to the appropriate number of significant figures. Part C kind of continues in this vein. You're basically going to measure you're going to kind of use, let's say, a measuring cup in this example here to measure out 1 quart, and you're going to see like how much that comes up to in milliliters. So, if you pour that into a graduated cylinder is how we would do this in lab. But to be honest with you, most measuring cups also have metric units on them. So if your measuring cup at home in your kitchen has milliliters as well, basically fill up your measuring cup up to the 1 quart mark, and then also read that same level using the milliliter markings on that same measuring cup. Okay, and go from there. So that's the experimental factor you're going to get here. For part C1, this one's just from that table. Here, actually, let me scroll up and show you what I'm talking about. So if we go back to the pre-lab, they have a table which lists a lot of common conversion factors. So for example, 1 liter is equal to 1,000 milliliters. Okay, that's the equality that relates those two quantities. We can then write those out as conversion factors. You can take these two pieces of your equality and write them as two possible fractions. 1 liter for every 1,000 milliliters, or 1,000 milliliters for every liter. Okay? So you're going to use one of these two conversion factors if you were to convert from liters to milliliters. and you would use the other conversion factor to go from milliliters to liters. Okay, so this table on page 3 is going to be very useful when we do part C of this lab report. Okay, so if we go back to part C on page 10, so over here when it says what's the equality, well, this is just copied from that table, that 1 liter is 1,000 milliliters. And if we were to write this out as a conversion factor, we would write out two fractions, two conversion factors, where each of these halves of the equality would be the numerator and denominator of our fraction. So we would have 1 liter for every 1,000 milliliters, and we would also have 1,000 milliliters for every 1 liter. Okay, so that's our those are the two conversion factors we would try to write out for this problem. So for part C2, the experimental factor over here is where we are measuring this using a measuring cup in our kitchen. So you grab a measuring cup, pour 1 quart of water in there, okay, and figure out how many milliliters that would be in your measuring cup. Okay, now for the true equality, you are getting this number over here from that table in your on page 3 of your pre-lab, where if you look it up, it says that 1 quart is 946 milliliters. Okay, and you would write those conversion factors again the same way. You would have 1 quart per 946 milliliters. Okay, or you could write that backwards. You could have 946 milliliters for every 1 quart. Okay, so now that if you want to answer this question over here, how does your experimental factor compare to that conversion factor? All they're asking for is that numerical comparison. So whatever this number winds up being when you measure this using your measuring cup, really just asking like, is it greater? Is it smaller? Is it about the same? Is it really close to the number? Is it really far off? That sort of thing. Hopefully you should have a number that's relatively close to 946. But again, even if you don't, it's not the end of the world. That's, you're going to have some experimental error. You're going to be off by a little bit when you try a problem like this. And that's completely normal. It'd be kind of weird if you didn't, actually. So don't stress too much about that. Okay. So I think you can continue on with part C3. You would be taking a piece of computer paper, just a regular sheet of white paper, and measure its length in inches using a ruler, and then measuring it in centimeters, and accordingly doing that comparison, using the experimental factor. And then you would look up the true equality, which on that table on page 3 would tell you that 1 inch is equal to 2.54 centimeters. And so, you want to see what, you can write that out again as a conversion factor. It would be 1 inch for every 2.54 centimeters, or 2.54 centimeters for every 1 inch. Those would be your two conversion factors. And again, the experimental factor, how does the comparison work? When you do your comparison here, right? So whatever your number of centimeters are and your number of inches are, okay, you're writing that here, those two actual numbers. So this number divided by this number is equal to some decimal. You're going to see how does that decimal compare to 2.54. That's the comparison we're doing over here. Okay. With part C4, I think there is a, oh wait, there was a typo somewhere in here. Hold on, let me see if I remember where that was. I think they must have fixed that. Oh, I think it was actually in the instructions. Let me go back to the instructions. Oh yeah, here, they made a typo in the instructions. Here we go. Okay, so if we scroll back up to the instructions for part C3, even though part C3 is talking about length, the instructions accidentally say milliliters in a quart. I think they meant centimeters in an inch is what they meant. So yeah, that's kind of what they meant to do over here. That's just a little typo they made. So watch out for that. Okay. That brings us then to the last part, part D. Basically, you can just use your height in inches. So whatever your height is, for example, if you're 5'8", convert that into inches. So that would be 68 inches. Okay, and then using the conversion factor of 2.54 centimeters per inch, convert that into centimeters. And of course, show that calculation. This is a good example of how you would, um, you know, use a conversion factor. So I'll tell you what, why don't I run you through this so that you can see this example. Obviously, use your own height. I'm 5'8", so I'm going to use that number. But use your own height to do this calculation. So if I'm 5'8", that is 68 inches, right? So I want to convert that from inches into centimeters. How do I do that calculation? So 68 inches is my starting point in my calculation, and I want to figure out my answer in centimeters, right? So I need to multiply by a particular conversion factor that's going to get inches to cancel out and leave my answer in centimeters. So to do that, I want inches to disappear. So that's going to go onto the denominator of my conversion factor. And I want centimeters to wind up as my answer. So that's going to go in the numerator of my conversion factor. The reason for this, I probably talked about this in lecture as well, but the reason for this is that any quantity, or any unit for that matter, divided by itself will cause itself to cancel out. Okay, you see this in any fraction. That's why, for example, any number, so 2 halves is a whole, for example. 2 divided by 2 is 1. So in this case, inches and inches cancels out, and we're left only with centimeters, which is what we want. So let's put in the numbers that would go here from that equality. Well, we know that 1 inch is 2.54 centimeters. And so, and again, you don't have to memorize that number. That's in the table on page 3. Don't worry about memorizing conversion factors for English units. I'll provide those in a quiz or exam if you need them. Okay, but basically that's how we would enter this problem. We would set up this problem. So now, how do I plug this into my calculator? Well, 68 multiplied by 2.54 and divided by 1 is what number? Well, to do that, let's pull up our calculator. Okay, so 68 times 2.54 is 172.72. Now, that divided by 1 is still going to be 172.72. So I'm going to go ahead and write it down. Now, quick question here. How many significant figures should I give that answer to? Should I write 172.72? Notice that we now have to look at the number of significant figures for our values that are used in our problem and give our answer accordingly. So notice that the 6 and the 8 are the only 2 significant figures in my number 68 inches, right? So I would have to give my answer to 2 sig figs. So the answer would be the 1 and the 7 are significant. I would have to cut off that 2. Now the question is, basically, so that's, instead of that disappearing, I wouldn't write 17. I would put a placeholder 0 there, kind of like how we did in part A of this lab report with that number 533,000. Okay, we put in those zeros to show where that decimal point ought to be. Okay, so instead of writing 172.72 centimeters, I'm only going to have 170 centimeters. That's my height in centimeters. So I'll write that down. Okay, and likewise, when I want to convert this into meters, I would look at the conversion factor between centimeters and meters. So for example, so generally, if you look at that table on page 3, you will see that the relationship between meters and centimeters is that there are 100 centimeters in 1 meter. That prefix centi means 100th, if that helps you remember it. So we start off with 170 centimeters, and we want to wind up with meters. And so you've got to ask yourself, all right, am I multiplying or dividing by 100? Well, to determine that, we want to enter in our units and get them to cancel out. So centimeters over here, okay, is what we want to cancel out. So that's going to wind up on the denominator of our conversion factor. So that centimeters and centimeters cancel out. We want meters on the numerator because that's what we want our answer to be in. So as I pointed out earlier, 1 meter is 100 centimeters, which you can get that from your table on page 3, though these are metric units and you do want to get comfortable with what those prefixes mean. So knowing that centi means 100th of something, that's something I do expect you to eventually memorize. And we'll talk more about this in the lecture, or if you've watched the lecture video first, you've already seen this. That's something that you do need to get comfortable with. Anyway, my point here is that because this is on the denominator, that means we're dividing by 100. Okay, so 170 divided by 100 is 1.7 meters. Okay, now notice that 170 is 2 significant figures, right? That trailing 0 is not significant since there's no decimal point. If there were a decimal point, then the trailing 0 becomes significant. Anyway, this is 2 significant figures, and that's why our answer is to 2 significant figures. I'm going to head off the question that's going to pop up here. You're probably asking, wait a minute, isn't 100 only 1 significant figure? Well, any conversion factor you can't use a conversion factor to determine the precision of a number. Conversion factors are understood to be to have an infinite amount of precision. So when someone writes 100 centimeters for every 1 meter, that 100, because it's defined as such, it has an infinite amount of precision. It's really 100.0000000 ad infinitum. Okay? So anyway, my point here is that this is the answer. It should be 1.7 meters, also to 2 significant figures, just like all of our other numbers are. Okay? So, again, you're going to have to do this using your own height, not mine. So, go from there. Okay, that's it for this lab. If you have any questions, feel free to email me or your instructor if you're not one of my students. And yeah, good luck.